Welcome back, students. In this section, 7.3, we will address three main issues. One, step functions. Two, impulse functions. And lastly, the delta function. If none of those make any sense right now, that's okay. Let's unpeel the title of this section bit by bit. This is a very long section, so you may want to divide it up into 2 or 3 sittings. Just as a quick note. Okay, let's begin. Section 7.3. Let's begin with the first topic, the topic of step functions. Okay, so often we encounter forcing functions in our differential equations that are applied from some point on in time. That is, as I've got drawn here for you guys, the forcing function is 0 for the first a seconds or hours or whatever of time, and then all of a sudden the forcing function is, if you will, switched on. So I would like a way of designating these functions in such a way that using the Laplace transform, or taking the Laplace transform of these sort of switched on functions, does not involve piecewise functions. So if that didn't make sense, let's look at a specific example. Suppose we're looking at a forcing function in the ty plane that's simply y equals t. Okay, so what that would look like is pretty predictable. What y equals t looks like is simply a line through the first quadrant. Of course, we're assuming here that the time is greater than or equal to 0. So here's what y equals t looks like. This is the situation. If this were a situation where the forcing function was given here as y equals t, then we would consider the forcing function switched on immediately. Immediately meaning time equals 0. The forcing function's in play. Now suppose we want to change things up a bit. Suppose we'd like to model the forcing function y equals t, but we would like to turn this on or switch this function on at, say, t equals 2. So what we'd be interested in would look pretty much like what we have, but it would look like y equals 0 for the first 2 seconds. So if that didn't make sense, let me just draw it for you here. So here's y equals t. So this is y equals t. The same y equals t as above. But I'm assuming that this forcing function is applied from time equals 2 seconds forward. So for the first 2 seconds, in time, there is no forcing function, or the forcing function is y equals 0. So let's draw in y equals 0 heavily here so it shows up. So y equals 0, and we'll put a little circle around t equals 2, and then right at t equals 2, the line y equals t is turned on, if you will, or switched on. Or if this were a mechanical force, the force was the external force of y equals t was applied right at 2 and then left on for t greater than or equal to 2. So in terms of writing out this function algebraically, we would use a step function, just as usual. The y value is 0 as long as t is between 0 and 2, and it's y equals t for t greater than or equal to 2. There's nothing wrong with expressing functions in piecewise form, but as I indicated a couple minutes earlier, I'd like a way of designating this function without using a piecewise function, in such a way that I can use a formula for the Laplace transform of the function without having to look at it in piecewise form. So if that still doesn't make sense, here's where we're heading with this. I would like to take my original function, y equals t, the first function drawn. Here's t equals 2, here's t equals 1. And I would like to, if you look back at the drawing, the first drawing, for time between 0 and 2, I would like to multiply that function y equals t by 0. I'd like to multiply y equals t, only for t between 0 and 2, by 0. If I do that, that'll give me y equals 0, the net result y equals 0 for t between 0 and 2. And then for t greater than or equal to 2, I'd like to take the function y equals t and multiply it by 1. That is, leave it unchanged. Okay, if you will, this is what I'd like to do. Let's take a look at the original function once again. So, give me a second here. Here's our original function once again. Y equals t. And right below that, I'm going to draw another function that kind of reflects what I was talking about, that multiplying by 0 or multiplying by 1 business. So here, right below it, I'm going to draw another function, and that function is going to look like this. It's going to be y equals 0. I don't know why that picked up here. Give me a second here, and I'll get rid of that hexagon that suddenly appeared. Okay, so we have y equals 0 for t between 0 and 2, open circle. And there goes there it is. I think it'll stop doing that, but okay. And then at t equals 2, and for t equals 2 greater than 2, I'm going to graph y equals 1. Okay, so y equals 0 for t between 0 and 2, and y equals 1 for t greater than or equal to 2. And right above on the graph of y equals t, I'm going to mark off t between 0 and 2. Now, imagine that we multiply the first function by the second function. Imagine if we multiply the first function, y equals t, by the second function. Well, let's see what happens when we do that. So I'm going to draw another axis here instead of axes. So I'm going to take two cases. First case is going to be t between 0 and 2. So the first function is y equals t. So if I multiply the first function, y equals t, by the second function, y equals 0 between 0 and 2, what's the net result going to be? It's going to be y equals 0. So I'm going to get y equals 0 for t between 0 and 2. And this is the result of taking y equals t and multiplying it by the second function, 0. Now let's look for t greater than 2. If t is greater than 2, I'm going to get y equals t times y equals 1. First function times second function. So the net result then for multiplying the first times the second for t greater than or equal to 2 is I'm going to get y equals t times 1, which is y equals t. So the first function is y equals t. The second function is y equals 0 for t between 0 and 2, and 1 for t greater than or equal to 2. And the last function is what I get by multiplying those two functions together. I'm going to rename the second function. I'm going to give you a brand new symbol for the second function. The second function is called a unit step function. I'll write that out in a second. And we designate it by u. Give me a second here. Let me draw a better u. U sub 2 of t. This is called a unit step function. Unit step function. Pretty clear why it's called a step function. It's called the unit step function because the maximum y value is 1. And a unit step function always looks like this. It's always 0 for time between 0 and some number, and then y equals 1 for time more than or equal to that number. So the last function then, the last function that I've got drawn then is then y equals t, y equals t times u sub 2 of t. Okay, so I can write my result, the result of a forcing function that turns on at t equals 2 and stays on, as a single closed expression. I don't have to look at as above the function expressed as in piecewise form. That becomes kind of important kind of soon. So I highlighted in red what the function would look like above if we used the piecewise function form, and I'm going to highlight below the better form, which allows me to write our function without using piecewise functions. Okay, so let's dig into this step function and see how it helps us with a lot of these physical situations where functions are switched on, then switched off, and then different functions are switched on and off, and so forth. So let's define this unit step function more precisely. Okay, so for what I'd like to do now is define this thing called a unit step function. The unit step function doesn't always turn on at 2. The unit step function is one that we say turns on at t equals a, and we designate that by u sub a of t, and it's a very simple function to identify. It's 0 for the first a seconds, so for t between 0 and a, and 1 from t equals a on forward. Okay, and so this function is very, very easy, and it helps us. You'll see how it really helps us out with some of these amazing problems soon. So the unit step function is simply y equals 0 for time between 0 and a, and then it's y equals 1 for time t greater than or equal to a. Okay, so let's work with this unit step function and ultimately work toward differential equations whose forcing functions, solving differential equations whose forcing functions are not always starting at 0, the ones that start at some time forward. Okay, so here's some practice. So for example, let's sketch a u sub 1 of t times cosine of pi t. Let's see what that looks like. Okay. Well, let's kind of remember what cosine of pi t looks like. So from trig, cosine of pi t, a real simple function to graph. It's just a cosine function. It's a cosine function that looks really squiggly. So here's y equals cosine of pi t. The period of this function, you remember the period of this function is 2 pi over the coefficient of t. So the period of that function, this function is 2. So this is what the function would look like from the point of view of a trig student without the unit step function involved. So the unit step function u sub 1 of t is 0 for t between 0 and 1, and 1 for t greater than or equal to 1. So what this does is it takes our graph and it makes it y equals 0 for the first second. Let me redo my axes here. Let's see. Now here it's y equals 0 for the first second. So if this is t equals 1, it's y equals 0. This is the effect of multiplying cosine pi t by u sub 1. And then at t equals 1, it's u sub 1 is 1. So multiplying 1 by our function above then just gets us the cosine graph, but starting at t equals, the graph actually starting at t equals 1. Okay, and of course the graph goes on and on. So if we were to continue the graph, it would go on and on and on. Both graphs would. Okay, let's take a look at another one. Let's sketch B. Y equals u sub 1 of t again times the cosine of pi times t minus 1. So this is a bit different. Notice that the functions are similar. They're very similar, but I've replaced cosine of pi t with cosine of pi times t minus 1. And remember from pre-calc and from trig that the effect of replacing t with t minus 1 is to shift the graph of the function to the right by 1. So imagine shifting the cosine of pi t to the right by 1, and leaving it, if you will, switched off for t less than 1. So here's t equals 1. Here's the cosine of pi t for t between 1 and 2. Give me a second here. The cosine function. I might not have this correct. Yeah, the period is 2, so this isn't quite right. Let me redo this graph. Let's see. Okay. Extend the x-axis, t-axis a little bit more. So here is the correct graph. This is what I'm graphing now, is y equals pi times t minus 1. But I haven't drawn the graph for t between 0 and 1 because multiplying by u sub 1 of t between for t between 0 and 1 gives us 0, and 0 times anything is 0. So the effect of multiplying the shifted cosine by u sub 1 is to shift the cosine function over to the place at which we're turning the function on. If that didn't make sense, that was a big chunk to chew. If that didn't make sense, let's take a look at what happens more generally. suppose we're looking at y equals a function f of t times u sub a of t. Okay. And remember what that does is it takes the graph of the function between 0 and a and brings it down to y equals 0. So let's say this is the shape of the function between 0 and a, and let's say this is the shape of the function afterwards. So what it does, multiplying a function by u sub a of t, is it makes the function between 0 and a, replaces it with y equals 0, and then literally turns on the function at t equals a. So it's 0 for t between 0 and a, and then for t greater than or equal to a, you got the function. Now imagine that instead of doing this, we want to shift the original function that starts at 0, shift it over to t equals a, and then turn it on. So to do that, we would take the original function and replace t with t minus a. That shifts the function over to the right by a units. And if we multiply that by u sub a of t, it leaves y equals 0 for the first a seconds. So let's graph that. The original function is graphed above, y equals f of t. But simply by multiplying f of t by u sub a, it just knocks off the function between 0 and a and brings it down to 0. Now assume I want to take that whole function that's graphed up there, included the dotted part, and I want to turn it on at t equals a. That is, I want to take that dotted part, the whole function, dotted part and solid part, and move it over and leave the function as y equals 0 for t between 0 and a. So I want to, effectively what I'm doing is I'm shifting the function f of t to the right by a and then turning it on. Okay, leaving it shut off between t equals 0 and a. Shut off meaning y equals 0 for t between 0 and a. Okay. So let's look at some more. Let's look at another example. Suppose I want to look at sketch y equals t minus 3 squared u sub 3 of t. Okay, so what this means graphically is that at least from the factor u sub 3 makes sure that the function is y equals 0 for the first 3 seconds. So here's 1, t equals 1, t equals 2, t equals 3. 1, 2, 3. So the result is going to be y equals 0 for t between 0 and 3. But then at t equals 3, we're going to graph the parabola y equals t squared, the one that's centered around the y-axis, but we're shifting it to the right by t equals 3. So right at t equals 3, we're filling in that dot and drawing the parabola y equals t squared, but shifted to the right by 3. Okay. Let's take a look at some more. Let's take a look at, for example, sketching y equals, let's say, u sub 1 of t minus u sub 2 of t. Okay. So let's do this bit by bit. I want to graph u sub 1 of t and u sub 2 of t. Then I'm going to graph the difference, u sub 1 minus u sub 2 of t. So give me a second to get these graphs done. Try to grow them a little small so they show up. So here's, let me draw 3 axes here. I guess I could have stopped the video to do this. That's okay. Say, yeah, oops. Let me undo what I did there. Okay. There we are, a third axis. Okay. So, on the first set of axes, I'm going to mark off t equals 1. And then I'm actually going to mark off t equals 2 as well. In fact, let me spread things out a little bit more. Here's, oops. Oh my goodness. Okay. So here's t equals 1. Here's t equals 2. So here's u sub 1 of t. It's y equals 0 for t between 0 and 1. And it's y equals 1 afterwards for t greater than or equal to 1. And then let's graph beneath that u sub 2. 1, 2. U sub 2 is 0 for the first 2 seconds, not including this t equals 2. And then for t greater than or equal to 2, it's y equals 1. Okay, now that's u sub 2 of t. Now let's create the graph u sub 1 minus u sub 2 of t by subtracting these two graphs. But let's break this down into looking at time between 0 and 1, then time between 1 and 2, then time greater than or equal to 2. So just concentrate on the t-axis for both the above graphs, on the t-axis for time between 0 and 1. On the first graph, if t is between 0 and 1, you're looking at y equals 0. The second graph, if t is between 0 and 1, you're looking at y equals 0. The third graph, then, the difference of those two, which should be 0 minus 0, which is 0. So you're going to get 0 for t between 0 and 1. Now between 1 and 2, things change up in the first function. For t between 1 and 2, for the first function, u sub 1 of t is y equals 1. For the second function, it's still y equals 0. For the third function, which is the difference of these two, remember the third function I'm graphing is the one that I wanted to graph initially, my actual problem. It's u1 minus u2 of t. And between 1 and 2, then I'm looking at y equals 1 from the first graph minus y equals 0 in the second graph, and that gives you y equals 1. As a result, 1 minus 0 is 1. Okay, and we'll circle at t equals 2. Now, to finish this off, let's look at t greater than or equal to 2. On the first graph, y equals 1. Second graph, y equals 1. Third graph, the difference of those two things, 1 minus 1 is 0. Okay, so it's like this graph. It looks like the t-axis that has had a segment cut out of it and lifted up 1 unit. So it's 0 for t between 0 and 1, 1 between t equals 1 and 2, and then 0 for t greater than or equal to 2. Okay? I would like to be able to get this graph much more quickly by looking at the original equation. So right now, with me, focus on the original equation. I'm going to write it out, spread out a little bit, and I'm going to insert in green some things here. I'm going to write this as plus 1 times u sub 1 of t. That just means u sub 1 of t. And then minus 1 times u sub 2 of t. It's the same function. It's just u sub 1 of t minus u sub 2 of t. Now here's where it gets really interesting and how we can do this really quickly. Think about the sign, the plus or minus sign that separates the terms, the u's, the unit step functions in this case, as being plus means turn on or switch on, and minus means turn off or switch off. So plus means turn on. The first plus means turn on, and what we turn on is y equals 1 at t equals 1. So the plus means turn on. The fact that this is 1 times u sub 1 means turn on y equals 1 at and we're looking at times u sub 1 at t sub at 1, and then leave it on for a while. That means for a while means from t equals 1 to some point, and then turn off. Oops, I'm going to be consistent with myself here. Turn off y equals 1 at t equals 2. At t equals 2. Okay, this is how we approach these graphs involving step functions in general. So let's take a look at some more examples along these lines. Okay, so here's our next example. I'm going to draw a graph, and I want to write an equation for this graph in terms of unit step functions. Okay, so write in terms of unit step functions. And here's the graph. So the graph, oops, the axes, and the graph looks like this. It's 0 for the first 2 seconds. It's y equals t for the next 2 seconds, and then it's y equals 0 for t greater than or equal to 4. So let's take a look at that more carefully. For the first 2 seconds, the function is y equals 0, so the dotted part of the graph is not the actual graph. For the first 2 seconds, it's 0. Then for t between 0 and 4, or 2 and 4 rather, the graph is y equals t. Oops, and then at 4 there's a circle up top. And then for t greater than or equal to 4, the graph is again y equals 0. Okay. Circle up here. My circle's gotten too solid. Okay, so it's y equals 0, y equals t, and back y equals 0. It's amazingly simple to write this, the equation of this graph without using piecewise functions. Okay. Now, imagine that the curve that's being turned on and turned off is simply y equals t. Where is y equal t being turned on? We are turning on plus y equals t at t equals 2 seconds. Plus means turns on. Y equals t is the function we're turning on. U sub 2 indicates we're turning it on at t equals 2. But then we're going to shut off, turn off that same function. Turn off means subtract. The same function, y equals t, at what time? T equals 4. And that's the equation of that function. Of course we don't have to write the plus t. We can simply write t u sub 2 of t minus t u sub 4 of t. Okay, let's do this for a few more functions, just for some practice. We're going to call this first example part A. Here's part B. Part B is pretty much as simple a function to draw. Okay, so for the first 2 seconds, y equals 0, just as before. Then for the next 2 seconds, we're looking at a line. And I, on purpose, didn't tell you the equation of the line. And then we're turning off that line at t equals 4 and leaving it off forever afterwards. So then it's y equals 0 again for t greater than or equal to 4. So here's our function. So the only thing we really need to do this is the equation of the linear part between 2 and 4. What is the equation of that line? It's real simple. The equation of this line is y equals, well, it has a slope of 1. If we go over 2, then we go up 1. So it's got to be y equals something t. But then it goes through the point 2, 0. So if we subtract 2, then that works out. Y equals t minus 2. When t equals 2, y equals 0. When t equals 4, y equals 2, which is what should be happening at the top part of our function here. Okay, so look at how simple it is to write the equation of this graph, this curve, without using piecewise functions. So it's y equals 0 for the first 2 seconds, but then we're turning on plus y equals t minus 2, t minus 2, so plus t minus 2. When are we turning it on? At t equals 2. But we're not leaving it on forever. We're shutting off, so minus means we're shutting off. What are we shutting off? The same function, t minus 2, t minus 2. When are we turning it off? At t equals 4. And since we're not turning on any other functions, that's the equation. That's the equation of this function. Let's take a look at one last one before we move on. C. So here's our axes again. And it's t versus y, just as before. So also just as before, in the first 2 seconds, our curve is y equals 0. First 2 seconds. Then between 2 and 4, just like above, it's y equals t plus 2. Plus 2. Let's see here. So here's 2. And then we're t greater than or equal to 4, it's y equals 2. Okay, so this, our graph sort of looks like this ramp. Okay, so let's do this. It is incredibly simple. I keep saying that, but it's incredibly simple to set up these functions where you have functions turning on and functions turning off using step functions. So what's going on? It's y equals 0 for a while. How long? 2 seconds. Then what's happening at t equals 2? At t equals 2, we're turning on t minus 2 when at t equals 2. Then we're turning off. When are we turning off y equals t minus 2? Remember, y equals t minus 2 is just this, the portion of the sloped part of the ramp. Then we're turning off that. Turning off means subtract. That same y equals t minus 2 when at t equals 4. But then, right at t equals 4, we're turning on another function. Turning on means add, so we're turning on. What are we turning on? Y equals 2, so plus 2. And when are we turning it on? At t equals 4, use of 4 of t. Okay. Now I've left the previous solutions unsimplified. Most of the time we want to carry out the carry through some simplifications. So we would, and you'll see that in a few minutes, we would write this as u sub 2, t minus 2 times u sub 2 of t minus t u sub 4 of t plus 2 u sub, this is just algebra, I'm just distributing the u sub 4 and the minus signs, plus 2 u sub 4 of t. So we would write this as t minus 2 u sub 2 of t minus t times u sub 4 of t plus 4 u sub 4 of t. Okay. The main idea, though, in this example is to be able to use step functions to write out a function. I'm going to do one more. I think it's important. You can always skip through examples if you've had enough. I think you should look at everything, but here's our next example. Again, the directions are the same, and I'm going to need some negative y values here. So here's an ax. Here's our set of axes. I want to fix this. Do better than this. I'm going to set up so I don't need any negative axes. I'll just draw in the negative axis. So, okay. Part D, in the first 2 seconds, I want to not have 0, but I want to actually have a non-zero function. I want to have y equals t in the first 2 seconds. So notice that our graphs on the left portion of our graph generally have a solid dot. The right portions of our little segments have open dots. That's something throughout. That happens throughout. So between 0 and 2, it's y equals t. Between 2 and 4, so here's 3, here's 4, it's y equals negative 1. So on the left-hand endpoint, it's solid. Right-hand endpoint, circle. For t between 4 and 5, the graph is y equals t minus 4. So the previous was y equals negative 1, and the first one's y equals t. Then open. But the graph at t equals 5 is going to continue on where the graph between 4 and 5 left off. So we're going to fill in that solid. and I'm going to replace it with an exponential function. Y equals e to the minus t, but shifted to the right by 5. And this is true forevermore. So for t greater than or equal to 5. So this is a complicated looking function. Using piecewise functions, this would look terrible. It would have four separate pieces, different intervals of time, and so forth. But it's real simple. It's real simple to get a formula for this graph using step functions. So here goes. So y equals t. Y equals t is immediately turned on. So there's no need to use step functions for that. We just say y equals t. But we're shutting off y equals t at 2. Shut off means subtract. What are we turning off? Y equals t. When are we turning it off? At 2 seconds. Simultaneously, we're turning on the next segment between 2 and 4. Simultaneously, we're turning on, so add. What are we turning on? Y equals -1. When are we turning it on? At t equals 2. How long are we leaving it on? For 2 seconds. So we're shutting it off, so minus. What are we shutting off? Y equals -1. When are we shutting it off? At t equals 4. Simultaneously, at t equals 4, we're turning on, between t equals 4 and 5, we're turning on y equals t minus 4. Turning on means add. What are we turning on? Y equals t minus 4. When are we turning it on? At t equals 4. Are we leaving it on forever? No. We're shutting it off. Minus. What are we shutting off? Y equals t minus 4. When are we shutting it off? At t equals 5. So times use of 5. Is that all? No. At t equals 5, we're turning on our last function. So plus, turning on. What are we turning on? We're turning on the exponential function e to the negative t minus 5. When are we turning it on? At t equals 5. So multiplied by use of 5 of t. And are we ever turning that off? Nope. So that's our function. Look at this long string of unit step functions. It looks terrible, but it's much worse if we had to use piecewise functions to do this. So I'm going to simplify this. This is t. And we have a couple of u sub 2 terms. So if we combine the t u sub 2 with the minus 1, u sub 2, it looks like minus the quantity t plus 1 times u sub 2 of t. And now we have a couple of u sub 4 terms. It looks like we have a plus 1 times u sub 4 and a plus t minus 4 u sub 4. So it looks like we have a total or a net result of, say, minus 3. That's plus 1 minus 4 plus t u sub 4 of t. And then we have a couple of u sub 5 terms. It looks like we're going to get a plus 4, a minus t, and a plus e to the exponential term, e to the minus t minus 5 times u sub 5 of t. Okay, and that would be really the shortest expression for this piecewise function that has 4 pieces in it. Okay. Now let's get to the reason for the season here. We would like to take Laplace transforms of these functions involving step functions. The whole idea is, remember that we're creating these functions with unit step functions so that we can model our forcing functions in differential equations that involve switching on forces, switching off forces, turning on voltages, turning off voltages, etc., etc. So I would like a formula. I would like a formula for the Laplace transform of a function that is turned on at some point t equals a, and the function that's turned on is a shifted version of f of t. That is, if my function f of t, say, looks like this, I'd like a formula for the Laplace transform of this function. If this is f of t, I'd like a Laplace transform, a nice simple Laplace transform formula for u sub a of t, f of t minus a. Okay, and of course I'm leaving it off here, but it's assumed that y equals 0 for the first a seconds. So let's do it. I'm going to derive the formula for you. You're not responsible for the derivation, but you might find it interesting. So here's the derivation for the formula for the Laplace transform of u sub a of t times f of t minus a. Let's use the definition of Laplace transforms. Laplace transform of a function is the integral from 0 to infinity of e to the negative st times the function. The function is u sub a of t, f of t minus a dt. Okay. Now that looks like a pretty complicated integral, but it's really not. Look right above the integral. There's the function graphed, u sub a of t times f of t minus a. It's 0 for the first a seconds. So for the first a, we can break this down into the integral from 0 to a of e to the minus st times 0 dt plus the integral the rest of the way from a to infinity of e to the negative st times f of t minus a. Okay, remember u sub a only has the value of 1, so u sub a times the function f of t minus a is just f of t minus a. Well, that reduces just to the second integral. This is just the integral from a to infinity, of e to the negative st times f of t minus a dt. I'm going to make a u substitution. I'm going to let u equal t minus a. If u equals t minus a, that means t equals u plus a. Take differentials. That means dt equals du. Now let's transform the integral into the new variable u. Well, when we make a u substitution in a definite integral, we have to make sure that we transform the limits of integration as well. So in the original integral, t starts at a. Well, if t equals a, that means u equals 0. T equals a, that means u equals 0. When t equals infinity, now look at the substitution, u equals t minus a. At the upper limit of integration, the new variable u equals the old variable t infinity minus a. Well, infinity minus a is still infinity. So the upper limit of integration is still infinity. Oops. I want to put like that in a nice black. And if you didn't see how I got that lower limit of integration, if t equals a, then that means u equals a minus a. Substitution is t minus a. That means 0. Okay, so make the substitution into the integrand. So this becomes e to the negative t equals, e to the minus s times t equals u plus a. T minus a is u. dt is du. Okay. So this becomes the integral from 0 to infinity. E to the minus su, e to the minus as or sa, f of u du. Now that e to the minus as does not depend on the variable with respect to which we're integrating. So it's constant according to with respect to the variable of integration. So it can be factored out. If you can hear my dog barking or not. So e to the minus su f of u du. Now look at that last integral. The variable of integration does not affect the value of a definite integral. So those u's could be replaced with t's, and that's just the Laplace transform again. So this is an e to the minus as times the Laplace transform of small f of t. Okay? Okay. So I want to pull all this together. If you're not interested in the proof at all, just concentrate on the net result. The net result is that the Laplace transform of u sub a of t, f of t minus a, is e to the minus as times the Laplace transform of the function small s, but not shifted, the unshifted version. Okay, this can also be written as the Laplace transform of u sub a of t, f of t minus a, f of t, ugly t minus a, is e to the minus as times capital F of s, where capital F of s is the Laplace transform of small f of t, not shifted. This result has a special name. You notice that it takes the Laplace transform of a shifted function. We've seen this type of thing happen before. And when we did, we called it the first shifting theorem. Well, this is called the second shifting theorem. So what's in red is called the second shifting theorem. Second shifting theorem. We'll review what the first shifting theorem looked like in a second or so. The second shifting theorem says the Laplace transform of u sub a of t times the shifted function f of t minus a is e to the minus as times the Laplace transform of the unshifted f of t. Okay. Okay. So let's use this. Let's do a couple of examples here. All right. So example. Again, if you don't remember what the first shifting theorem looked like, we'll be using both very soon. So for example, find the Laplace transform of f of t. Part A. I'm assuming that the function f of t given in piecewise form is y equals 1 for a while. So for t between 0 and 4 pi, not including 4 pi. And then it becomes cosine of t minus 4 pi. That's a shifted cosine to the right by 4 pi for t greater than or equal to 4 pi. Okay, so that's the function whose Laplace transform I'm after now. Let's graph the function. We're going to need to write our function in terms of unit step functions, and I think it's really convenient if we have a graph of the function. So here's the function. For a while, it's y equals 1. So for a while, it's simply y equals 1. How long? For the first 4 pi seconds, it's y equals 1. Then all of a sudden, it's y equals a cosine function shifted to the right by 4 pi, starting at 4 pi. Okay, well, this cosine function has a period of 2 pi. So I'm going to graph one period of this cosine function for t between 4 pi and 4 pi. So that hollow dot then gets filled in. This function is continuous. And we're looking at the cosine function then, picking up for t greater than or equal to 4 pi. Okay, so there's a graph of our function, and it doesn't stop at 6 pi. It just continues on and on and on and on and on. However, looks like I changed the amplitude of our function. It goes on and on and on with the same amplitude of 1. There. Okay. So we want the Laplace transform of this function. Somehow this function is going to end up on the right-hand side of some differential equation as a forcing function. We would like its Laplace transform. Well, I'm going to rewrite f of t using step functions. So the function is y equals 1 turned on immediately. So there's no step function involved here. It's y equals 1. But we're shutting off y equals 1 at t equals 4 pi. So we're shutting off y equals 1. So we're shutting off y equals 1 at 4 pi. I'll leave I can write the of t's in there. I don't have to be sloppy. So turn on y equals 1 immediately, shut off y equals 1 at 4 pi. But right at 4 pi, simultaneously, I'm turning on the cosine function, t minus 4 pi. When am I turning it on? Times use of 4 pi of t. Okay. Okay, so I'm going to find the Laplace transform of this function now. The second shifting theorem, just to remind us, the second shifting theorem says the Laplace transform of u sub a of t times a shifted function to the right by that same a, t equals a, is e to the minus as times the Laplace transform of the unshifted small f of t. Okay, so let's dig into our function. So the Laplace transform of f of t, our function f of t, is, let's do term by term. The Laplace transform of y equals 1 is 1 over s. There's no shift involved. There's this old-fashioned Laplace transform from before. So now we're going to dig into the Laplace transform of the second term. The Laplace transform of the second term, well, the second term is u sub 4 pi of t times 1. U sub 4, let me write this in. I think it'll make it more clear. So minus the Laplace transform of u sub 4 pi of t times 1. Okay, and then plus the Laplace transform of u sub 4 pi of t times cosine of t minus 4 pi. Just adding an extra step in here. So we get 1 over s minus the Laplace transform by the second shifting theorem of u sub 4 pi of t times 1 is e to the minus a. A is 4 pi here. E to the minus as times the Laplace transform of 1. Laplace transform of 1 is 1 over s. Plus the next Laplace transform of u sub 4 pi times cosine of t minus 4 pi is e to the minus 4 pi s times the Laplace transform of the unshifted cosine of just the Laplace transform of cosine of t, which is s over s squared plus 1. Okay, and that's our Laplace transform. Okay, let's take a look at another example. B. In this case, I'm going to give our function. I'm not going to graph it. I'm just going to give it to us. The function is f of t is u sub pi of t times cosine of t. That's it. The function is u sub pi of t times cosine of t. We have a little problem here. We have a little problem here. The problem is that the second shifting theorem says I'm finding the Laplace transform of u sub a of t times a function that's shifted to the right by t minus a. Our function is u sub pi of t times an unshifted cosine. That's a bit of a problem. U minus as times the Laplace transform of the unshifted function. The problem is that cosine of t is not a shifted function. I need to replace cosine of t with a shifted function. I'm going to do that with a little trick. Okay, and believe me, it really is a very little trick. So u sub pi of t, without taking any Laplace transform, cosine of t is the same thing as u sub pi of t. I need this function cosine to be shifted to the right by pi. So I'm going to force it to be that way. Cosine of t minus pi. Now I've changed my function though. Well, then add pi to balance things out. Add pi to balance things out. Okay, and I'm going to use an identity from trig that deals with the cosine of a plus b. A being t minus pi and b being pi. Well, formula from trig is cosine a cosine b minus sine a sine b. Okay. So our function is u sub pi of t times cosine a t minus pi cosine b minus sine a sine b. It's pi here. The cosine of pi is -1. Sine of pi is 0. So our function then becomes minus u sub pi of t times the cosine of t minus pi. This step, as annoying as it is absolutely necessary. In order to use the second shifting theorem, we need to have u sub a of t multiplied by a shifted function to the right by a, by the same amount in the subscript of u. So now we can do this. Now it becomes very simple. So the Laplace transform of f of t becomes the Laplace transform of minus u sub pi of t times the cosine of t minus pi. And we can use our second shifting theorem. The minus factors out. The Laplace transform of u sub pi times a function is e to the minus pi s times the Laplace transform of the unshifted cosine times the Laplace transform of just cosine of t. So this becomes minus e to the minus pi s times s over s squared plus 1, which is fine. We could write this as minus s e to the minus pi s over s squared plus 1. Okay. Well, with differential equations, we're not just interested in Laplace transforms. We're interested in inverse Laplace transforms. So I'm going to work an inverse Laplace transform for us. And this example is pretty much as rough as it gets. So this is going to be an involved example, but it doesn't get much tougher than this. So here's our next example. Okay. Example. Find the inverse Laplace transform of, let's see, s minus, my s's keep looking like 5s. S minus 4 e to the minus 3s all over s squared minus 4s plus 5. Okay. All right, so let's dig in. To do this, in order to do this, I think I'm going to write out our shifting theorems. We're going to be using both the first and second shifting theorems. So the first shifting theorem, just to remind you, first shifting theorem looks like the Laplace transform of e to the at times f of t is f, capital F, of s minus a. Okay. In reverse form, in inverse Laplace transform form, it says the inverse Laplace transform of capital F of s minus a is e to the at, and small f of t is the inverse Laplace transform of capital F of s. Okay, so there's both the forward direction, backwards direction, Laplace transform, inverse Laplace transform direction for the first shifting theorem. The second shifting theorem. The second shifting theorem, the one from the current section, says the Laplace transform of u sub a of t times the shifted times f of t minus a, so function shifted to the right by a, is e to the minus as times capital F of s. Okay. And if you just look at the second shifting theorem and compare with the first, they look so similar, but they are very, very different. The reverse form is the inverse Laplace transform of e to the minus as times f of s is u sub a of t times the inverse Laplace transform of capital F of s, but that's evaluated at t minus a. And the versions we're going to use for our example of both these theorems are going to be the reverse versions. So we're going to use the first shifting theorem in reverse, and we'll use green for reverse, reverse meaning inverse Laplace transform, and we'll use green for the second one as well. Here we are. Okay, so let's dig in. Notice that the inverse Laplace transform that we're hunting for has an e to the minus 3s in it. That's the a in the second shifting theorem would be 3. So let's dig in. So the inverse Laplace transform of our function e to the minus, I'm going to rewrite it so it looks like I can directly apply it the second shifting theorem. E to the minus 3s times s minus 4 over s squared minus 4s plus 5. That's equal to, now look at the second shifting theorem, green version, reverse version, it's u sub 3 of t times the inverse Laplace transform of the rest of the function, s minus 4 over s squared minus 4s plus 5. But that final result for that inverse Laplace transform is evaluated at t minus 3. Okay. Okay. So the big task for us is to evaluate that inverse Laplace transform within the capital L inverse there. So what I'm going to do is I'm going to use the technique that we used in a previous section. So this becomes, the u sub 3 is just going to follow us along. So this becomes u sub 3 of t. And I'm going to, because I can't factor the denominator very easily, I'm going to complete the square. So this is old news for us. S minus 4. S squared minus 4s minus 5. If you complete the square, reduces to, or turns into s minus 2 squared plus 1. Okay. Now notice that we have in the denominator that perfect square s minus 2. So I'm going to manipulate my numerator to contain that factor as well, or that term as well. So this is u sub 3 t times the inverse Laplace transform of, I'm going to write the numerator as s minus 2 again. Bear with me. S minus 2 in the numerator, minus 2 again, pause if you need to convince yourself of my result. I've split my s minus 4 over s minus 2 squared plus 1 into s minus 2 over s minus 2 squared plus 1 minus 2 over s minus 2 squared plus 1, but I've turned that into negative 2 times 1 over s minus 2 squared plus 1. If you need to, you can stop the video and pause it to convince yourself of what I did. Okay, but I did it very deliberately. So now I'm gonna to finish off the inverse Laplace transform of these two terms by using the first shifting theorem. Look at the first shifting theorem in green above. It has to do with finding the inverse Laplace transform of a shifted Laplace transform. So we're looking at u sub 3 of t. I'm going to be directly applying the first shifting theorem to this times e to the at, where a is 2, e to the 2t times the inverse Laplace transform of the quantity without the shift. Inverse Laplace transform of s over s squared plus 1. Okay. Minus 2 times applying the first shifting theorem to the second inverse Laplace transform. This is e to the also e to the 2t. First shifting theorem says e to the at, a is equal to 2, times the inverse Laplace transform of the unshifted Laplace transform, s squared plus 1. Okay, again, feel free to pause the video to convince yourself of these steps. Okay. And let's continue. This is evaluated at t minus 3. I neglected that from our work above. So go a few lines above. So this is evaluated at t minus 3. This is evaluated at t minus 3. This is evaluated at t minus 3. Okay, so continuing. This is u sub 3 of t times e to the 2t, the inverse Laplace transform of s over s squared plus 1 is cosine of t, and minus 2 e to the 2t times the inverse Laplace transform of 1 over s squared plus 1 is the sine of t. All of this is evaluated at t minus 3. Okay, the final result is u sub 3 of t. I can factor out the e to the minus 2t, but this is going to be evaluated at t minus 3 times the cosine of t evaluated at t minus 3. That means cosine of t minus 3 minus 2 times the sine of t evaluated at t minus 3. And that is our inverse Laplace transform. This particular example is a very important one. This is the type of inverse Laplace transforms that will occur in homework as you go through solving differential equations. So this is a good model for you. So our next example is really why we're here. We're learning Laplace transforms so that we can solve the types of differential equations that occur in STEM fields, in either physics or engineering mostly, but in STEM fields more generally. So we're going to solve a differential equation using Laplace transforms. I want to solve the first order differential equation. Y prime minus y on the left equals f of t, and y of 0, so it's an initial value problem actually. Y of 0 is 0, with f of t as pictured. So I'm going to draw our forcing function. So here goes. Here's our forcing function. I'll need an axis. I'm going to need some negative y. It looks like a constant 1 for a while. This won't be to scale, that's okay. Well, I could fix this. I can make it to scale. So y equals 1 for a while. Then for t after 1, it's a line with a slope of negative 1. This is 2. Okay, so this is our forcing function. It's a piecewise function. But I would like to be able to, I'd like to be able to write our forcing functions so that we don't use piecewise functions, because we have a formula for Laplace transforms involving step functions. So I'd like to write this forcing function in terms of a step function. Now notice that for the first second, the forcing function looks like just a constant y equals 1. And then it becomes linear. I need the equation of that linear portion. The linear, it can be done very, very quickly. You could do this methodically. You could use the point slope form of a line, or you can notice that the line has a slope of -1. If I move over 1 in the x direction, I move over, in the t direction, I move over -1. Down, I go down 1 in the y direction. So the slope is -1. So the equation should be y involving -t, but it goes through 2, 0. So 2 minus t will work out nicely. If you let t equal 2, you get y equals 0. If that doesn't work for you, that's okay. You can notice the slope is -1, and it goes through the point 2, 0. And you could use y minus y naught equals m times t minus t naught. Y minus 0 equals -1 times t minus 0. T minus 2, sorry. Fix that up. So y equals -t plus t, or 2 minus t. Okay. In any case, I'm going to write f of t using step functions. So initially, the function y equals 1 is turned on, if you will. So there's no need to use a unit step function if the function is not 0 for the first 1 second, or any number of seconds. You just write the function. But then we're turning off y equals 1. Turn off, so that means subtract. What are we subtracting? Y equals 1. When are we subtracting? When are we turning it off? At t equals 1. Then simultaneously we're turning on. Turning on means add. What are we turning on? 2 minus t. When are we turning it on? At t equals 1. Okay, so let's simplify this. This becomes 1 minus u sub 1 of t plus 2 u sub 1 of t minus t u sub 1 of t, or 1 minus 1 u sub 1 plus 2 u sub 1 is plus 1 u sub 1. This is plus u sub 1 of t minus t u sub 1 of t. I'm going to factor out the u sub 1, but I'm also going to factor out a minus sign. That'll become clear why I'm doing that in a minute or so. So I'm going to, in fact, I'm going to write this even better. Okay, so 1 plus u sub 1 of t, and I keep doing the same mistake over and over again. So let's see if my service will let me fix this. I'm going to factor out a minus u sub 1 of t times t minus 1. Sorry that took so long. So I'm not just factoring out the u sub 1 from the last two terms, I'm factoring out a minus. And the reason for that is the second shifting theorem requires f of t minus a to be multiplied by u sub a. Okay. If that's still not clear, it will be in just a few seconds here. So my differential equation takes on the form y prime minus y on the left equals 1 minus u sub 1 of t times t minus 1. I'm going to take Laplace transforms of both sides. Take Laplace transform of left equals Laplace transform of right. T minus 1. Using our formulas from a previous section, Laplace transform of y prime is s times the Laplace transform of y minus y of 0 minus the Laplace transform of y. That takes care of the left. On the right, Laplace transform of 1 is 1 over s. Now I'm going to invoke the second shifting theorem. Says Laplace transform of u sub a of t, f of t minus a, is e to the minus as times the Laplace transform of small f not shifted. So minus e to the minus a equals 1. So e to the minus 1s, or e to minus s, times the Laplace transform of the unshifted function. Okay, or 1 over s minus e to the minus s, Laplace transform of t is 1 over s squared. Okay, back on the left-hand side, notice that our initial condition was y of 0 equals 0. Our initial condition is y of 0 equals 0. So let's put that in. Let's factor in on the left. Let's factor out the Laplace transform and the s minus times s minus 1. Y of 0 is 0. Right? And let's isolate our Laplace transform. Laplace transform of y, then dividing both sides by s minus 1 is 1 over s times s minus 1 minus e to the minus s times 1 over s squared times s minus 1. Okay, so now let's dig into the inverse Laplace transform. So let's do this. In order to do this, we're going to need some partial fractions, and I'm not going to show the partial fractions work on video. So the first expression, 1 over s times s minus 1, has a partial fractions decomposition of 1 over s minus 1 minus 1 over s minus e to the minus s. The partial fractions decomposition of the second of the term 1 over s squared times s minus 1 is 1 over s minus 1. It's also going to have 1 over s, so minus 1 over s. It's also going to have 1 over s squared minus 1 over s squared. Okay. And I go one step further here. So the Laplace transform of y then is 1 over s minus 1 minus 1 over s minus e to the minus s times 1 over s minus 1. I'm distributing the minus e to the minus s through. Minus s times 1 over s. Again, in fact, I'm distributing in minus e to the minus s. So plus over s squared. All right. Now I'm in a position to find inverse Laplace transform. Inverse Laplace transform of 1 over s minus 1 is e to the t. The inverse Laplace transform of 1 over s is 1. Now, back to the second shifting theorem. The second shifting theorem says that the Laplace transform of u sub a of t times f of t minus a is e to the minus as times f of s. So the reverse form is the inverse Laplace transform of e to the minus as times capital F of s is u sub a of t times f of t minus a. F of t minus a, small f of t minus a, means the inverse Laplace transform of capital F of s, but that evaluated at t minus a. Okay, so we're going to use the green form. So minus, then, continuing on with our inverse Laplace transform. The a is 1, so u sub 1 of t times the inverse Laplace transform of 1 over s minus 1, but that evaluated at t minus 1, plus u sub 1 of t times the inverse Laplace transform of 1 over s, but that evaluated at t minus 1, plus u sub 1 of t times the inverse Laplace transform of 1 over s squared, but that evaluated at t minus 1. Okay. T minus 1. So let's continue. So let's skip on down over here. So we're almost there, believe it or not. So this is e to the t minus 1. The inverse Laplace transform of 1 over s minus 1 is e to the t, but that's evaluated at t minus 1. So minus u sub 1 of t, e to the t, but evaluated at t minus 1. Okay. Next, plus u sub 1 of t, the inverse Laplace transform of 1 over s is 1. Okay. Evaluated at t minus 1 is still 1. Okay. Plus, finally, u sub t, the inverse Laplace transform, oops, not u sub t, u sub 1. That was strange. U sub 1 of t, looks like a 0. U sub 1 of t, inverse Laplace transform of 1 over s squared is t, but that's evaluated at t minus 1. T minus 1. That's our solution. I'm gonna simplify this just a tiny bit. So this becomes e to the t minus 1. And let's say I want to write this as u sub 1 of t times e to the t minus 1. And I believe the u sub 1 of t times 1 cancels out, leaving us just with minus t. And it is minus t since I factored out the u sub 1 of t. And this is our solution. It's a very, very powerful technique for solving differential equations. For a more elaborate problem, if there is such a thing, there is. For a more elaborate problem, you might want to see example 1 on page 360. It's a second order differential equation where the partial fractions are a little more sticky and stuff, but I wanted to keep to a fairly simple example for the video presentation. Okay, so I want to start the last part of the section. You might want to take a break if you haven't had one so far. We finished about 2/3 of the section. The last part of our section has to do with what are called impulse functions, and also something real mysterious, probably to most physics students, only having had maybe a couple years of physics, something called the delta function. And let's just go ahead and get started with an example here. Let's consider two problems. Let's consider case one of the two problems. Case one. The problem goes like this. A mass is pulled down, or is pulled from equilibrium and released, and satisfies a particular initial value problem. So let's start with that. A mass is, let's say, pulled, how do we want to do this? Let's say 1 meter from equilibrium. My dog is playing with a toy in the background. It's not me squeaking. And released. So we have this mass hanging from a spring that's hanging from a ceiling, and the mass is pulled 1 meter from equilibrium and released. And it satisfies, let's say, the initial value problem. So this is really referring us back to, I guess, section 4.5. The initial value problem looks like this. Y double prime plus y equals 0. It's pulled down 1 unit from equilibrium and released. So released means we're not helping it out with any initial velocity, so the initial velocity is 0. So our spring mass system looks like this. Okay. Let's solve the initial value problem. Solving the initial value problem. This is an old problem for us. This isn't new. Let's take the Laplace transform of both sides of the equation. So, in fact, let's do this from scratch. Let's take the Laplace transform of y double prime plus y equals Laplace transform of 0. So our formulas tell us that this left-hand side becomes s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0 plus the Laplace transform of y from the second term equals 0. The initial conditions are y of 0 is 1 and the initial velocity is 0, so the thing was released instead of helped out. So this tells us if we factor out the Laplace transform, we get s squared, a Laplace transform times s squared plus 1 equals s. So the Laplace transform of my solution is s over s squared plus 1. So my solution is the inverse Laplace transform of s over s squared plus 1, which is the cosine of t. This should make a lot of sense. Let me move my spring mass system down a little bit, and then we can look at it. So if the spring mass system is pulled 1 meter down from equilibrium and then released, so here's equilibrium, so it's pulled down 1 meter and then released. Remember in section 4.5 we call the positive y direction down. Then we can expect, if we were to graph the position versus time, or displacement versus time, that our object should trace out a cosine function. If we were to allow a separate t-axis in here, we would expect our position function to sort of look like this. Okay, so if we were to, again, flip y to be positive in the upward direction for us, we would expect to see something like the cosine function, and our solution to the differential equation or the initial value problem kind of verifies that. Okay. And in this problem, we were assuming that there was no frictional loss, no external forces acting on the object. The only thing that started this thing in motion was the initial displacement of 1 meter from equilibrium. Okay, so I want to change things up a bit. Case 2. Case 2 is where things get really interesting. So case 1, plain old case from section 4.5, neglecting wind resistance, really kind of a simple case. Case 2 involves an external force that is not studied really in physics courses until advanced level physics. The external force we're going to apply is going to be applied at time t equals 2 seconds. And the best way to describe this force now is to just say that at 2 seconds I'm going to hit the object, hit the mass with a hammer. So the mass in case 1 is hit, and I'm gonna have to put hit in quotations here, because to hit something with a hammer really produces a forcing function that's not encountered in early physics, at least first couple of years of physics. So the mass in case 1 is hit by a hammer at t equals 2 pi. Now, just imagine this. You have your spring mass system just as before. And here is a graph of the spring in the first 2 pi seconds of its motion, about 6.28 seconds of its motion. And right here at t equals 2 pi, you hit the mass. You imagine hitting the mass. What is that going to do with the object? I mean, just think about this intuitively. If the mass is bobbing up and down, and at t equals 2 pi, at the exact moment when it reaches its maximum distance away from equilibrium, you smack it. What you might expect is a sharp departure from its position at y equals 1, but you also would probably assume that after it regained its composure, so to speak, that I want to redraw this. It would continue its motion in the form of a trig function. So you smack it at this point. I wanted to draw a sharper kind of behavior at the graph. You smack it, and you would tend to think, and correctly so, by the way, that after the blow with the hammer, that the object is going to continue on in a sine or cosine, because it's still acting only under the influence of the restorative force from the spring and possibly to that of gravity. But so you would expect that it would return to a sort of normal sine or cosine motion. In order to be able to model this force, though, we have to leave behind the standard normal functions that we learn about in up through all the calculus courses. So what's going on here? And I know this seems kind of silly to draw, but I'm going to do it anyway. We're imagining that at t equals 2 pi, so we're looking at the mass or the brick or whatever that's attached to the spring, and we're imagining striking it, and I'm only drawing this for effect, striking it, this is my best drawing of a hammer, by the way. With a hammer in the upward direction with some sort of force. An object that's hit by a hammer is given what's called, and this is what the name of the force is for our section, it's given an impulsive force. It's a force that is extremely, extremely large in magnitude, but is only imparted over an extremely, extremely small amount of time. I want to consider graphing that idea. So here's my representation, or a representation, of what this impulsive force, or the magnitude of this impulsive force, is supposed to be. The impulsive force is, now just think about this. If you hit a nail with a hammer, the force is experienced, if you will, by the force of the hammer is experienced by the nail over an extremely short time interval. In fact, you can regard the amount of time that the nail, if you will, or the mass that's hanging from the spring experiences this force to be infinitely small. But also you can imagine that the force that's imparted at this time t equals 2 pi is infinitely large. This explains something kind of interesting about sort of a really, really brief side trip about the force applied by coin dies at the U.S. Mint. When coins are being made, small blanks in the shape of a quarter or whatever kind of coin you're making are put into position. Small blanks, and that's the name of the unprinted, if you will, quarters or whatever, are placed in the die. The die, when it comes down and smacks that blank, hits the die with such force that the blank is not carved. The face of George Washington in a quarter is not carved into the metal blank. When the die hits the metal blank, it imparts such a force that the metal actually melts instantaneously, and melts in the form of the face imprinted on the die. So the force is well, it's not infinite, is extremely, extremely large, but that die hits the blank almost instantaneously. So that's a good model of approximately what an impulsive force would be. It's the same kind of thing that's going on with a hammer. When you hit a nail on the head, the temperature of the tip of that nail grows tremendously. So why doesn't it melt? The best explanation I can come up with, and this isn't my explanation. This explanation came from a physicist. The explanation is that the force is applied in such a small amount of time that the tip of the nail head doesn't have a chance to melt into liquid. In fact, apparently the tip of the nail, or the nail head, does begin to melt, but it's so brief that it solidifies almost instantaneously. Okay, so the idea is that an impulsive force is huge, infinitely huge, mathematically, and occurs instantaneously. So what does it look like? So here's a graph of the impulsive force that we're giving to this mass at t equals 2 pi. So at t equals 2 pi, there's t equals 2 pi. Before t equals 2 pi, there's the magnitude of the force imparted by the hammer is 0. There's no contact of the object by the hammer. At 2 pi, the force is infinite. This is supposed to be vertically upward, is infinite. But right after 2 pi, the force is back to 0. this is not a function in the sense of the functions you learn and start learning in pre-calculus all the way through calculus 3. This is a very, very strange function. The most interesting thing about this force to me is that while it's impossible to write an equation for the force, the Laplace transform of this force is really manageable and very simple. This is one of the more amazing places in applied mathematics for me. Before we get to the Laplace transform of this force, though, we need to back up a little bit and define some terms. Some of these terms are probably well known to you. If you've taken physics 201, 202, or 203, you've probably been exposed to the concept of an impulse. So what is impulse? Okay, so suppose, to define this term impulse, suppose that f of t, not the f of t that I've graphed above, but some other forcing function that doesn't act instantaneously. Suppose f of t acts on an object over a particular time interval, over the time interval, let's say from t1 to t2. Okay. The impulse of this force, which we call I, is I equals the integral from negative infinity to positive infinity of f of t dt. Okay, that is the area underneath the forcing function over the entire t-axis. Remember, if a function is non-negative, then the definite integral of the function captures numerically area. Okay, so let's compute this quantity, and maybe let's relate it to something from physics that you might be a little more familiar with. So what does our force function look like? The force function looks like this. The force function acts on an object over the time interval only from t1 to t2. So here's our force function. Let's say it's open here, then 0 everywhere else. Let's say it's 0, force is 0 from 0 to t1. So let's say this is our force function acting on the object. Okay, so the impulse is the integral from negative infinity to infinity of this function, forcing function. Well, the forcing function is 0 except for between t1 and t2. So this integral becomes the integral from t1 to t2 of f of t dt. Okay, so I'm going to do something that our textbook doesn't do. I'm going to relate this concept of impulse to something that's I think it's covered in either Physics 201 or 202 or both. I'm going to use Newton's second law here. Newton's second law says that the force acting on the object is equal to the mass times the acceleration of the object. And the mass times the acceleration is the mass times the time derivative of velocity. Okay? Now let's simplify the integrand a little bit. This integrand can be written as the integral, or the integral can be written as the integral from t1 to t2 of m dv. Kind of consider the dt's as canceling. Well, if the mass is constant, then this just becomes mass times velocity of t from t1 to t2. So let's complete the fundamental theorem of calculus here. This is the mass times the velocity at t2 minus the velocity at t1. I want to ask those of you who've had first couple semesters of physics, do you recognize this quantity? Well, if you don't, let's write the velocity of t2 minus the velocity of t1 as the change in velocity over that time interval. And mass is constant. Let's get it inside the delta. So this looks like the impulse is the change in mass times velocity. And we learned in early physics that mass times velocity is momentum. So we can view the impulse of a force over a time interval from t1 to t2 is nothing more than the change in momentum over that same time period. Okay. Now we want to model a very, very special force, that force that I have graphed above, which is 0 everywhere except for 2 pi when it's infinite. The typical smacking the hammer on the nail or the mass spring system type force. Okay, we want our force, the one we're considering, to satisfy a couple of very specific things. We want our force to satisfy two things. One, f of t acts instantaneously. That means it acts at only one time value. And this is what makes it difficult to do with regular functions. We want the function to have unit impulse. Unit means 1. Unit impulse. We want our function to have an impulse of 1. But how can that be for any function? For a function to act instantaneously means that t1 and t2 is not an interval, but it's a point, and the impulse is the area underneath that point, and the area underneath the point is always going to be 0, so how could it be unit impulse? The way this force is created is really kind of brilliant. So let's design a unit impulsive force that satisfies these two things. Let's start with the second thing first. The second thing, that a force that has unit impulse. This is very easy to construct. Let's let d sub epsilon, this is the Greek letter epsilon, of t minus a, don't get lost in the symbols here, it's really not too difficult when you get into it. Let's let d sub epsilon of t minus a equal this function. It's 1 over epsilon times u sub a of t minus u sub a plus epsilon of t. And let's examine this. Let's examine what this force looks like. Okay, let's tear it apart. So d sub epsilon of t minus a, if I distribute the 1 over epsilon through, looks like 1 over epsilon u sub a of t minus 1 over epsilon u sub a plus epsilon of t. Let's graph this. Let's graph this force. This is not the unit impulsive force, but it's going to get us there. So remember, the unit impulse force u sub a is 0 all the way up to a, and then it's 1. Just the unit step function u sub a. But remember, we have an additional interpretation of these unit step functions as switching on and switching off. So the way I've written out d sub epsilon is that it looks like initially 1 over epsilon is turned on or switched on at A. So let's give 1 over epsilon this value on the y-axis. And that value is switched on at t equals A. Okay, so the 1 over epsilon times u sub A looks like 0 up until A. Then it's 1 over epsilon from A to A plus epsilon, where epsilon is just some small positive number. But then at A plus epsilon, 1 over epsilon is shut off. So look back at our just above at the d sub epsilon. In green, I'm going to put just before, right after the equal sign is plus. That means turn on 1 over epsilon at A. Then right after that, we're subtracting, and I'm going to do this in green, which means shut off or turn off 1 over epsilon at A plus epsilon. So we expect this to be just sort of a lump, a vertical lump in the t-axis. And then from A plus epsilon on, it's 0. This is not an impulsive force. An impulsive force needs to act only instantaneously, and this acts in the interval from A to A plus epsilon. However, this function does have unit impulse. Unit impulse. It's very easy to see that. The impulse of this function is the integral from A to A plus epsilon. Actually, to be much more precise, the impulse of this function is the integral from negative infinity to infinity. That's the definition of impulse of f of t dt. But most of this function is 0. Most of the forcing function is 0. The only portion of the function that remains is between A and A plus epsilon. And the y value there is 1 over epsilon. Numerically, or we can see from, just apply the fundamental theorem here, the antiderivative of 1 over epsilon dt is 1 over epsilon t, and this goes from A to A plus epsilon. And this is nothing more than 1 over epsilon times upper limit is A plus epsilon, subtract the lower limit A. This is 1 over epsilon times epsilon, which is 1. This means unit impulse. We could have very, very easily seen that without even looking at this as an integral. The impulse equals the area. The area is the base. On the base, what's the distance from A to A plus epsilon is epsilon. Okay, so it's the base times the height. Well, what's the height of this thing? It's 1 over epsilon, which is just 1. Okay, and in either case, we've created a force, d sub epsilon, which imparts unit impulse. Now, the mysterious, the really strange part about this force that we need to actually create for ourselves from this, is that we need a force that doesn't act over an interval from A to A plus epsilon. We need it to act only at one point. So we need it to act only at epsilon, at A. So acts instantaneously This doesn't. So how can we get this d sub epsilon to be an impulsive force, one that acts only instantaneously? Well, look what happens as epsilon is allowed to get smaller and smaller and smaller. Look what happens to the graph of this function, of this forcing function, as epsilon is allowed to shrink. Here's A plus epsilon. Here's 1 over epsilon. So here's what our function looks like for a particular value of epsilon. So let's make epsilon smaller. If epsilon is smaller, let's say A plus epsilon is now right about here. I still need to make sure that I capture 1 unit of area. So if epsilon is made smaller, that means 1 over epsilon is going to be made bigger. We'll have to, because we have to keep 1 unit of area in this, underneath this forcing function. So make epsilon smaller still. Let's say A plus epsilon is now about right here. If A plus epsilon is now in this position, that means the height of this thing, which is 1 over epsilon now, is going to have to be made substantially bigger. The smaller epsilon is chosen, the taller this little rectangle has to be chosen. So how do we create this function? The answer is we let epsilon approach 0. So let epsilon approach 0 through positive numbers to get the impulsive force. Impulsive force. Then the force will act instantaneously. Look what's happening to the graph of our rectangle as epsilon approaches 0. As epsilon approaches 0, the rectangle is growing taller and taller and taller and taller and skinnier and skinnier and skinnier and skinnier. So what we're going to do is we're going to define this force. This is the force after we've let epsilon approach 0 as the Greek letter, this is a small Greek letter delta of t minus a. That is the limit as epsilon approaches 0 of those d sub epsilon of t minus a's. Okay, that is, it is the forcing function that looks like this. It's 0 everywhere except at A when it's infinite. That's the best way I can imagine graphing this thing, and it's not any kind of a real force that we've ever seen. However, this delta satisfies 2 things. Delta t minus a satisfies the 2 things we needed. 1, the delta is 0 for t not equal to a. What's it equal to when actually t equals a? It doesn't matter. It's infinite. It's infinite. This delta satisfies that this function is 0 for t not equal to a. That's how we constructed it. We let epsilon approach 0. So no matter what t you put in, eventually that's not equal to a, that epsilon will be no matter what, how do we say this? Look back to our drawing. No matter what t you choose, let's say t is chosen right here. Epsilon can be made so small that a plus epsilon is on the left of it, making the delta at that t equal to 0. That's not the best way I can put that. The second thing it satisfies is that the integral from negative infinity to infinity of the delta dt is 1. The second thing is unit impulse. We have imparted a unit impulse, or in physics 200 lingo, a change in momentum of 1. And the first part says that it acts instantaneously. It acts only at one point. Okay. So what's our next step? Remember, we started out the second part of this lecture with a physical problem. We want to model the motion for the spring mass system that's been in motion for up to 2 pi seconds, and then right at 2 pi we hit this mass with an impulsive force. So we need the Laplace transform of this delta force. So here's the definition of the Laplace transform of the delta force. This delta force, by the way, is very often called a delta force, but more specifically, it's called the Dirac delta. Paul Dirac was a person, a physicist, mathematician who contributed an enormous amount of work in mathematical physics in the beginning of the 20th century, including, I believe, modeling this function that bears his name. Okay. So the definition of the Laplace transform of the Dirac delta force is it's equal to the limit as epsilon approaches 0 of the Laplace transform of the d sub epsilon of t minus a's. Now remember, the d sub epsilons, those don't represent the impulsive force, so the force that acts instantaneously. They model the force that's given by the rectangular box, if you will, between a and a plus epsilon. So what we're going to do is we're going to find the Laplace transform of that rectangular, if you will, impulsive force. And then we're going to let epsilon approach 0 to get the definition of the Laplace transform of the Dirac delta function. Let's do it. This is equal to the limit as epsilon approaches 0. And of course, this is as epsilon approaches 0 through positive numbers of, well, let's substitute the d sub epsilon function. It's 1 over epsilon times u at a of t minus u at a plus epsilon t. Okay. Okay, let's keep going with this. This is now the epsilon. It doesn't depend on t, so the epsilon can be factored out of the Laplace transform. The epsilon is constant with respect to the Laplace transform operation or operator. So this is 1 over epsilon times u sub a of t, and I'm going to write this as u sub a of t times 1 minus u sub a plus epsilon of t times 1, and I'm going to use the second shifting theorem. So remind us, the second shifting theorem. Theorem looks like the Laplace transform of u sub a of t times f shifted to the right by a equals e to the minus as times the Laplace transform of the unshifted function. All right, so this is just a reminder to us. All right, so let's on with our problem. So this becomes the limit as epsilon approaches 0 through positive numbers, 1 over epsilon. So I'm interested in the Laplace transform of u sub a of t times 1. So the function of t minus a is 1. So the second shifting theorem says that this is e to the minus as times the Laplace transform of the unshifted 1. Well, 1 is 1 whether you shift it or not. The Laplace transform of 1 is 1 over s. Okay. Then the second term gives us, in the parentheses, gives us, using the second shifting theorem again, e to the minus a times s. Oh, sorry, that's not right. The a in this case is replaced with a plus epsilon. So this is e to the minus a plus epsilon s times the Laplace transform of 1, which is 1 over s. This limit looks more complicated than it is. Now that we're done with the Laplace transform operator, we concern ourselves with letting epsilon approach 0. So epsilon is now the live variable. So what I'm going to do is I'm going to try to factor from this expression as much stuff that doesn't have epsilons in it out. So we have 1 over epsilon times e to the minus a epsilon times 1 over s. Simplifying the exponential term e to the minus quantity a plus epsilon times s, we have e to the minus as e to the minus s epsilon times 1 over s. Okay. Now what I'm gonna do is I'm gonna factor out the e to the minus as over s out of the brackets, and I'm going to put the 1 over epsilon back into the brackets. I'll distribute it back in. So when I do that, I'm going to get 1 minus e to the minus s epsilon over epsilon. Okay, and if you'd like to pause the video to verify that would be fine. Alrighty, so the term or the factor with s and no epsilon in it is now constant with respect to the variable epsilon. So I'm going to factor it out of the limiting process. This becomes the limit e to the minus as over s times the limit as epsilon approaches 0 from the right for the positive numbers of 1 minus e to the minus s epsilon over epsilon. Now, let's see what happens when epsilon is allowed to approach 0. In the denominator, the denominator is approaching 0. The denominator is approaching 0. If you let epsilon approach 0 in the numerator, the exponential term e to the minus s epsilon approaches 1. E to the 0 is 1, and 1 minus 1 is 0. Now, I'd like you to think about that for a second. What does it mean when we're evaluating limits and we get a form 0 over 0? It means that we can use L'Hopital's rule to evaluate the limit. So this form is called indeterminate I think it's from Calculus 2. This is called indeterminate. And when we have this form, 0 over 0, we can use L'Hopital's rule to evaluate the limit. Now I'm going to write a little L apostrophe H above the equal sign before I write in the next step, just to indicate that I'm using L'Hopital's rule. And to remind you, you use L'Hopital's rule by replacing the function the indeterminate function by the quotient of the derivatives of the numerator and denominator. In other words, take the derivative of numerator and denominator and then let epsilon approach 0 again. Well, now we're taking a derivative not with respect to s, but with respect to epsilon. So the derivative in the denominator is 1. The derivative of epsilon with respect to epsilon is 1. The derivative of 1 is 0. And the derivative of e to the minus s epsilon with respect to epsilon is negative s. Okay. Now we can let epsilon approach 0 from the right, and we're taking the limit now of something that is no longer indeterminate. As epsilon approaches 0, e to the negative s epsilon approaches e to the 0, which is 1. The opposite of negative s is s, and we get, after all this work, that the Laplace transform of the Dirac delta function, delta of t minus a, is e to the minus as. While I'm not going to expect you to reproduce this proof or this derivation on a test, the result is something that you want to remember. This is huge for us. This is saying that the Laplace transform of the unit impulse function is e to the minus as. Keep in mind that the delta function is that quote-unquote function, delta of t minus a. It's that function that acts only at one point and is infinite. It's that forcing function that can be regarded as infinite at t equals a and 0 everywhere else. And its Laplace transform is very, 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 very simple. The Laplace transform of the unit impulse function is e to the minus as. Let's finish up this example by finishing our problem in case 2. Back to case 2. So, back to case 2. Case 2 involved, I'm going to take us back there. A little probably rough on your eyes to do this. But here's case 2. Case 2 is where, if you look at the focus on the picture on the left, is that the only external force for this spring mass system is at t equals 2 pi when we smack the mass in the negative direction. Remember, the positive y value is down. We're smacking this in the negative direction, negative y direction. So the differential equation, sorry about my screen here, folks. So the differential equation satisfied is y double prime plus y equals the impulsive force is acting opposite the positive y direction, so it's acting in a negative direction, and we're going to assume that we're going to apply 1 unit of impulse. What this means is that we're going to apply the Dirac delta, 1 unit of the Dirac delta force in the negative direction. This means that my external force is imparting a change in momentum of 1. We could have also insisted that the blow to the mass at t equals 2 pi insisted an arbitrary number of unit impulses. So we could have had y double prime plus y equals negative 17 times delta of t minus 2 pi, in which case we would have been applying a force an impulsive force that resulted in a change in momentum of 17. units of momentum, okay? So I'm just going to apply a change in momentum of 1, or an impulse of 1, okay? So the initial conditions don't change. Y of 0 is still 1. We still initially pulled this spring down 1. We let it go. We didn't apply any given initial velocity. But at 2 pi, this spring mass system was smacked instantaneously. Okay, let's solve this resulting differential equation. Let's take the Laplace let's take the Laplace transform of both sides. Actually, we're not solving a differential equation. We're solving a initial value problem. So let's solve this initial value problem. Okay, Laplace transform both sides. Laplace transform left side. Formula tells us Laplace transform of y double prime is s squared Laplace y minus s y of 0 minus y prime of 0 plus Laplace transform of y. Then we get to the interesting half of the equation. Laplace transform of the Dirac delta function at t minus 2 pi is e to the minus 2 pi s. E to the minus 2 pi s. So while we can't come up with an explicit formula for this delta function in terms of ordinary functions we're used to, its Laplace transform is quite an ordinary function. It's just e to the minus 2 pi s. Okay, again with a negative because we're smacking the mass in the negative direction. Okay, so let's continue on. The left-hand side simplifies just as it did before, factoring out Laplace transform. Y of 0 is still 1. Y prime of 0 is still 0. So on the right-hand side we have s. That's adding s to both sides, minus e to the minus 2 pi s. Dividing both sides by s squared plus 1, we get s over s squared plus 1, just like we did before, but we have that additional term, e to the minus 2 pi s times 1 over s squared plus 1. Okay, so y equals the inverse Laplace transform of the right-hand side, s over s squared plus 1, minus the inverse Laplace transform of e to the minus 2 pi s times 1 over s squared plus 1. Yeah. Okay, so the inverse Laplace transform of the first term is real simple. That just gives us our cosine. This is cosine of t. Now to get the inverse Laplace transform of the second term, again we invoke our second shifting theorem. The second shifting theorem says that in fact, I think I need to use, sorry about that, the second shifting theorem, but okay, sorry about that. The second shifting theorem, just to remind us, says that the Laplace transform of u sub a of t times f of t minus a equals e to the minus as times the Laplace transform of f of t, or e to the minus as times f of s. The backwards form, inverse Laplace transform of e to the minus as f of s equals u sub a of t times f of t minus a, which means u sub a of t times the inverse Laplace transform of capital F of s, but evaluated at t minus a. Okay, so let's apply that to our second term. So our second term is going to give us, since we have an e to the minus 2 pi s with a equal to 2 pi, it's going to give us u sub 2 pi of t times the inverse Laplace transform of 1 over s squared plus 1, but that evaluated at t minus 2 pi. Alrighty, so let me get my reminder out of our way. This says that y equals cosine of t minus u sub 2 pi of t. The inverse Laplace transform of 1 over s squared plus 1 is sine of t, but our inverse Laplace transform needs to be evaluated at t minus 2 pi. So that's our solution. I want to graph this solution. I want to look a little more critically at this solution. In order to do that, I want to get rid of the step function. So in a homework setting, this is how you would leave your answer the way I just wrote it. But I want to see what's happening physically with our result that we found theoretically. So our function, I'm just rewriting it here. Our solution is this. Now, the sine of t minus 2 pi, can you think of a simpler expression for that? The sine of t minus 2 pi, well, sine of t has a period of 2 pi. So if you remove 2 pi, the sine of t is not affected. So the sine of t minus 2 pi is the sine of t. Let's write this as a piecewise function. So this function is cosine of t minus, now u sub 2 pi is 0, so it's 0 times sine of t for t between 0 and 2 pi. But if t is greater than 2 pi, u sub 2 pi is 1. So we get 1 times sine of t for t greater than or equal to 2 pi. So let's do a little more with this. This then is the cosine of t minus 0 is the cosine of t for t between 0 and 2 pi. For t greater than 2 pi, the function is cosine of t minus sine of t. Now I'm going to use some fancy trig here, and you don't need to obsess over it unless you want to. But the fancy trig says that cosine t minus sine t can be written as a single cosine of t. Plus pi over 4. And this is where we get some really nice validation of our initial thinking of what should happen with the graph of the displacement if we include an impulsive force or smacking this thing with a hammer at 2 pi. Remember, the original thinking was that upon smacking the mass in the negative direction, or in any direction with a hammer, the amplitude of the resulting motion should be increased, and increased forever, since we don't have any friction involved here, and that ultimately the spring, the restorative force from the spring should take this back into a sine or cosine, and this is true. Let's graph this function. Let's graph the function briefly and approximately. Okay, so if t is between 0 and 2 pi, let's say this is 2 pi here. and this is 1, and this is -1. So t is between 0 and 2 pi. Now I'm being really careful about my graph. It's kind of important here. Between 0 and 2 pi. The function looks the way we'd expect it to be, just cosine. And that's just a reflection of the first part of the piecewise function. But when t is greater than 2 pi, we're looking at a cosine function now that has an entirely different amplitude. This is too big. The new amplitude after t equals 2 pi is radically different. So what has happened is when we hit the object with the hammer, we've created a sharp dip in the function at t equals 2 pi, a sharp change in the function. But we retain our periodic displacement function with a new amplitude and same period, but a new amplitude of square root of 2. Okay, so our theoretical model here that we created completely agrees with our intuition in terms of what should be happening graphically. Okay, all right. So the important, just to recap very quickly, just recap the ending of this. The impulsive force function delta has a Laplace transform of e to the minus as, and with that we're allowed to solve with the Laplace transform technique physical problems where we have impulsive forces as our forcing functions, that is, forces that act instantaneously only, but with infinite magnitude. Okay, and that ends this lecture for section 7.3, and I'm looking forward to talking with you all again soon.